In this lesson video, we're going to cover electric fields. Later in the course, we're going to look and see how similar these are to magnetic fields and gravitational fields. But for now, let's focus. An electric field is a field of force that acts on charged objects. All that means is that if we put an object with positive charge near another object with positive charge, there is a force between them. They repel. Magnetic fields act on objects with magnetism. Gravitational fields act on objects with mass. Electric fields act on objects with charge. The electric field strength is defined as the force per unit positive charge acting on a stationary point charge. Mathematically, that's E equals F over Q, but be very, very careful. That equation does not explicitly mention that the charge is positive or that it's stationary. The electric field strength is defined as the force per unit positive charge acting on a stationary point charge. So that's the definition, but it's not always that useful. Sure, if you know the field strength and you want to know the force and hence acceleration on an electron, for example, great. But what if you want to know the field strength? Unless you are working with elementary particles, it's actually quite hard to measure the charge. So we want another method, and luckily there's a very simple equation for parallel plates. Between the two plates, which have a potential difference V across them, the electric field strength is simply E equals V over D, the distance between them. That's fantastic because we can use a voltmeter and a ruler to measure those two very, very simply. So the electric field strength is defined by E equals F over Q, but we can also use E equals V over D. Your task now is to prove that E equals V over D. Starting with the defining equation E equals F over Q, show that E equals V over D. I suggest you pause the video and give it a go. I'm going to carry on now and I'll put up a separate lesson video with one proof in case you get stuck. So let's look at an example for a uniform electric field. These two plates have a PD of 400 volts across them. The separation is 8 centimeters, so the field strength is E equals V over D equals 400 over 0.08 equals 5,000 volts per centimeter, or 5,000 newtons per coulomb. Easy enough. Now let's consider a point halfway between now. What's the field strength here? Have a think. If I tell you the answer is 5,000 newtons per coulomb, can you explain why? Remember to pause and think if you're struggling. Well, the distance from this plate is now halved. It's only 4 centimeters. But the potential difference is also halved. At this point, halfway from the 0 volt plate to the 400 volt plate, the potential is only 200 volts. So E equals V over D equals 200 over 0.04 equals 5,000 newtons per coulomb. As I said at the start, this is a uniform electric field, so the electric field strength is the same throughout. If I do go and put a positively charged particle here, it will move toward the more negative plate. The force is going to be equal to F equals EQ, so it's constant. And with F equals ma, that means it will experience constant acceleration, much like falling in a gravitational field. That force vector I drew is actually useful as it shows the direction of the force inside the electric field. We actually tend to draw many of these and we give them various names such as lines of force, field lines, or flux lines. They go away from positive and towards negative. They tend to leave the surface at 90 degrees and they tend to spread out. In a uniform field, they're nice and simple, but as we get to the edges, they can start to spread out a bit more because they can. And if we look at other shapes for our charged objects, we get other patterns for the field lines. To sketch them, keep to the general principles I outlined a moment ago, and your pictures will approximately be correct. And that's all you need for now. So there we have an introduction to electric fields. In the future, we'll look at capacitors and we'll look at spheres and other non-uniform electric fields, but for now we've really covered enough. We understand what an electric field is and what effect it has on a charged particle. We know how to draw electric fields and with their field lines, and so we're now able to work with an electric field and understand mathematically what effect it will have on the world around it.